Hey there, I'm Benjamin. Today we are going to talk about the monotone convergence theorem. Now, just by looking at its name, let us try to predict something about its statement. We can see that the term monotone here would imply that this theorem involves functions, and the term convergence would imply that some kind of converging sequences are involved. So, a good assumption would be that this theorem gives us some kind of information on converging sequence of functions where either each function is monotonic or the sequence in itself is monotonic, or maybe both. Well, let's see. Let x m mu be a measure space and sequence fn be a sequence of non-negative measurable functions on x such that f and x converges pointwise to the limiting function f on x. Then the integral of the limiting function f over x with respect to mu is exactly equal to the limit of the sequence of integrals integral f and x over x with respect to mu. Now that's a lot to catch up to. So let's back up a little bit. So to clearly understand the statement, I want you to imagine these functions as some curves in R square. Say f1x, f2x, f3x, and so on, where this sequence of curves is monotonic, that is, the curve f2x is completely above the curve f1x, kind of like an envelope over the curve f1x. Similarly, the curve f3x is completely above f2x and f1x, and so on. Note that given a sequence of functions is monotonic does not mean that the functions in that sequence f1x, f2x, ... are monotonic functions. Furthermore, imagine that this sequence of monotonic curves in R square is tending towards a fixed curve as n tends to infinity. Then the monotone convergence theorem says that the integral or the area under that fixed limiting curve must be exactly equal to the limit of the sequence of integrals, that is the limit of area under the curves f1x, f2x, and so on. So what this theorem essentially does is that it gives us a condition for a sequence of functions in a measure space which, when satisfied, will enable us to freely move the limit inside and outside the integral of that sequence of functions. Let us look at its proof. Since fn converges to f pointwise for every point in x, and fn here is a sequence of measurable functions, then by this result, the limiting function f must also be a measurable function. Again, since fn here is a sequence of non-negative measurable functions that converge pointwise to the measurable function for every point in x, we can directly apply Fatou's lemma to get that the integral of the limiting function f over x with respect to mu is less than or equal to the limit infimum of the sequence of integrals integral fn over x with respect to mu. What we have done here is that we have successfully found an upper bound to the fixed value integral of f over x with respect to mu. Let us name this equation 1. Now, as the given sequence of functions is monotonic, as we discussed earlier, each of these curves must be below the fixed limiting curve. That is, fn must be less than or equal to f for every n belonging to the set of natural numbers. then, by this property of Lebesgue integrals over a measurable space x, we can confidently take the integral over x on both sides to get this new set of inequalities. So what we have here is a sequence of integrals where each integral is bounded by this fixed value. This would imply that the sequence of supremum of these integrals must also be bounded by that fixed value. Furthermore, taking the limit of this sequence, which is limit supremum of integral of fnx over x with respect to mu, must then also be less than or equal to the fixed value, which is integral value of f over x with respect to mu. Hence, we have successfully found that limit supremum of the sequence of integrals acts as a lower bound to the fixed value integral of f over x. This is in contrast with our equation 1, where we found the upper bound of this same fixed value to be the limit infimum of the sequence of integrals. Let us name this equation 2. So, since for any sequence an, limit infimum an is always less than or equal to limit supremum an. Hence, from equation 1 and 2, we get this satisfying inequality where the extreme left and right terms, colored in violet, are the same term, implying that all distinct terms in this inequality must be equal to each other. Finally, we have for any sequence an, limit supremum is equal to limit infimum is equal to a finite value, say capital L, if and only if the limit of this sequence itself is equal to capital L. Hence, in our case, that finite value, which is integral of f over x with respect to mu, must be exactly equal to the limit of the sequence of integrals, that is, the limit of integral of fn over x with respect to mu. This completes the proof. Thank you so much for watching this video. I appreciate it a lot. Feel free to add your feedback in the comments. I will see you again in the next one.